Research and development of an intelligent drone. In this framework, I will explain the design and software development methodology of an autonomous intelligent drone. The scope of this video will illustrate the evolution of an actual single passenger smart drone development. The conceptual design is based on a very scaled down, that is 24-inch smart drone model, in order to simulate at a system level, together with the artificial intelligence software models. The main objective is to ultimately build an actual full-scale intelligent drone with a payload capability of carrying a single person, as it is illustrated later on in this video. As you can see, I have developed the software models in my beautiful design center in the beautiful city of Medellin Software Valley. Medellin is characterized as being the best software district of technology in America, surrounded by the majestic emerald green mountains of South America. It serves as a source of inspiration. The first segment of the design methodology for the intelligent drone deals with all the characteristics of building a scaled down model, basically a 25-inch scaled down intelligent drone. Building the frame requires a lot of calculations and knowledge about materials. These include focusing on how to assemble all the different components of the current smart drone. Also paying close attention as to the thrust of the motor after mounting the motor on the frame. This is extremely important. It will tell you whether your drone will float in the air or fall down, because it is unbalanced. The formula for payload calculation is as follows. P is equal to T times M times H minus W. This is the basic formula. So, if P is the payload capacity of the drone, how much your drone can lift. M is the number of motors, and W is the weight of the drone itself, and H is the hover throttle percentage, and the thrust of the motors will be as follows. Here, the motors are arranged almost as if they lie along the corners of the imaginary square. Two of them rotate clockwise, while the other two motors on the other diagonal rotate anti-clockwise. The drone remains level by adjusting the power each motor is provided with. Normally, the main CPU board, central processing unit board, is used for three adjustments autonomously. The thrust each rotor produces allows the drone, the smart drone, to perform four types of movements, that is altitude, roll, yaw, and pitch. In addition, for more self-controlling principles, a barometer, a GPS, a sonar, and other components such as telemetry are integrated at the system level to integrate the intelligent smart drone. Therefore, the main components for building the autonomous intelligent drone are as follows: the frame, several motors, typically 4, the electric speed controllers, the propellers, the battery, the main CPU intelligent board, the inertial measurement unit IMU, the IRC controller as well, in addition to a GPS and perhaps a lidar detector system. The frame is the first unit. The frame should be strong and flexible to accommodate vibrations produced. The frame will have a mounting plate at the center holding all the digital electronic circuitries, 4 arms, 4 motor brackets to connect each motor to each arm, to the end of each arm. The motors, these motors are identical to traditional DC motors. They do not have any brushes. Make sure to check the RPM, revolution per minute. The motors can generate through the kV rating, that is RPM constant of a motor. The motors should rotate anti-clockwise to counteract the torque of the propellers. All the propellers will generate the necessary thrust for the intelligent drone, making sure that corresponding clockwise and anti-clockwise rotating pairs of propellers. For instance, as an example, for lifting more weight, then use a large diameter and pitch propeller. But if you want more RPM, to use smaller or mid-size propellers. If you want more stability for the smart drone, which will lift weights, then we'll use less RPM at the motor with more torque and higher pitch propellers. The electronic speed controllers control the speed of the motors. It has a battery input and a motor output with 3 phases, and it requires 4 for each motor. The maximum level of current the source will provide while the ESC also sees if the ESC is programmable to the needs. For example, if you want to change the signal. Now I will use the IMU, the inertial measurement unit. This board will measure the quad's orientation velocity, gravity, force, etc. and will level the drone. This unit consists of a 3-axis gyroscope to read angular velocity and accelerometer to measure acceleration and force. This type of combination is known as 6DOF-IMU. In this way, it senses the orientation of the quad. The flight controller is actually the onboard controller CPU. You can select the parts you wish to install and assemble in the controller itself, which is the main CPU controller. This concludes the synopsis and analysis of the hardware and artificial intelligence digital smart intelligent boards. That is all the CPU boards, the IMU, the ESC, and the gyroscopes. Now let's talk about the machine learning algorithms and the artificial intelligence software models that were used in the smart drone project. The main software model and modules include the wire.h library to establish gyroscope communications. It includes the EEPROM.h library to store info into the EEPROM. The following parameters are also performed and included. First, set up the PID gain and limit settings. That is the gain settings for roll P controller, gain settings for roll I controller, and gain settings for D or roll D controller, and also the maximum output of the PID controller. Now let's set the gain for the pitch PID, set the gain for the yaw for the PID controller. Next, declare all global variables for channels 1, channel 2, channel 3, and channel 4 in the EEPROM data high byte and low byte. Now let's set serial for 57600. Store the gyro address in the variable. Set the I2C clock speed to 400 kHz and start the I2C as master. Now let's configure the digital ports and turn on the warning LED checks, and then check the EEPROM signature. Now let's set up the MPU with the gyroscope plus the accelerometer, and now we're ready to set the gyro registers. Take multiple gyro data points, calibrate and read the gyro output. Include the roll pitch and yaw values. Now divide all the above values by 2000. So wait until the receiver is active and the throtter is set to lower positions. Set the digital ports, load the battery voltage, the gyro PID input in degrees per second, the gyro angle calculation, that is, calculate the travel PID and add to the angle pitch variable. Calculate the travel roll angle to the angle roll variable. Now calculate the accelerometer vectors and the accelerometer calibration values for pitch and for roll. Now let's talk about several subroutines within the main software controller modules. That is, subroutine for reading the gyro. Start the communications with the gyroscope. Set all registers and convert receivers for pitch, roll, throttle, and yaw. Compensate after calibration, and the subroutine to calculate the PID outputs, and now declare all local variables. I have illustrated the development of an artificial intelligence smart drone from original concepts to actual working prototypes. The flight tests and design verification took place in the spectacular city of Medellin Software Valley at the design centers. Medellin Software Valley is a city of approximately 3.9 million people in population, and it is characterized as being the epicenter for the fourth industrial revolution and also the best technology epicenter district in all of America, including the United States of America. Medellin was also declared the most innovative city in the world, declared by Citigroup and by Wall Street Journal and the New York Times. These are very powerful entities from the United States of America.